Now, Frank Wilczek, he got his PhD from Princeton University in 1974. He then stayed at Princeton as a faculty member until 1981, when he moved to the University of California in Santa Barbara, and when he was professor of physics and also the first permanent member of the Institute for Theoretical Physics in Santa Barbara. He then moved to the Institute of Advanced Study in Princeton, and then currently he is the Hermann Feschbach Professor of Physics at MIT. Now, Frank has received many honors for his work in physics. This includes, he was a Sloan Foundation Fellow, he was also a MacArthur Foundation Fellow. He has received the Dirac Medal, the Sakurai Prize, the Michelson Prize, the Lorentz Medal, the King Faisal Prize, and not least the 2004 Nobel Prize for the discovery of asymptotic freedom in the theory of strong interactions. Frank has written extensively both technical and non-technical articles about physics and life, the universe, and pretty much everything. And for his general science writing, he was also awarded the Lilienfeld Prize of the American Physical Society for science writing. But let me not keep you any longer, but please welcome Professor Frank Wilczek, recipient of the Oskar Klein Medal, which he can now add to this long list of honors. And so yes, please welcome Professor Wilczek.
Thank you very much. It's a great pleasure to be here. Brings back many memories. And coming from the Nobel Prize ceremonies this year, which was part of the inspiration for my topic today, it's a wonderful illustration of the unity of physics and its fertility, as you'll see, that ideas that were originally developed in the context of low-temperature physics and condensed matter physics turn out to describe the elementary interactions at the basis of the physical world, and that these ideas continue to inspire new thoughts, new, more sophisticated ways of thinking about matter, and I hope to exemplify that with some new ideas at the end. Let me start by reviewing the classics. This can be considered as a prequel to the Nobel Prize lectures of this year. I'd like to explore the roots of those ideas in condensed matter physics a bit. The simplest model for superfluidity involves a complex scalar field that supports a phase symmetry, that is mathematically a symmetry of the group U1, in its fundamental equations, but not in their stable solutions. This is the understanding of what superfluidity is that emerged successively over the years, starting really with the insights of London and Landau and Anderson, and becoming more sophisticated as time has gone on. This sort of theory describes the superfluidity of helium-4. In that context, the scalar field creates and destroys helium atoms, and the phase symmetry, the U1 symmetry that characterizes the model, is associated with the conservation of helium-4 atom number. So it's conservation of helium-4 atoms that's spontaneously violated in superfluidity. I'm going to use, throughout most of this talk, relativistic kinematics, because that's easier for me, and I don't want to complicate the ideas by hopping back and forth between relativistic and non-relativistic and introducing chemical potentials. So I will sacrifice some realism as the cost of elegance and simplicity. Anyway, in the context of this model, we have a potential. If we want to support spontaneous image breaking, we can do that very simply. If we have a negative mass squared, so an imaginary mass term for the scalar field, stabilized by a quartic interaction, a nonlinear interaction, then the minimum energy comes about when the scalar field develops a vacuum expectation value, and simple calculation shows that the magnitude of that vacuum expectation value should be the magnitude of the mass divided by the square root of the coupling. We can then erect the solutions, the stable solutions, that are not the most symmetric solutions. The most symmetric solutions, of course, would have phi equals 0. The expectation value destroys the symmetry, because if I make a phase transformation, any fixed value of the phi field changes. So expanding around a non-trivial vacuum, we isolate the V and look at small fluctuations around it. We can see what the oscillations around the stable ground state looks like. And the straightforward algebra, which I won't belabor here, is that if you plug in this expansion to the original simple scalar field model, the simplest possible scalar field model, you find that you get a massive field, this rho field, that corresponds to oscillations in the total amplitude of the, or density of the liquid, of the fluid represented by the phi field. You see that having expanded around the stable solution, now the mass is positive and equal to square root of 2 times mu, and there are some nonlinear interactions. The imaginary or phase part here does not appear in the potential because the potential was fully symmetric, but derivatives of it can come into play, and we get what looks like a kinetic energy for that field. A simple kinetic energy, if we ignore fluctuations in the density, including fluctuations in the density, introduces some nonlinear interactions. But basically, we have a massless excitation there. And that is very interesting, because if we study the low energy or low temperature behavior of our substance, the low energy excitations will dominate the behavior. So one has, therefore, these soft modes that correspond to motion within the ground state manifold. That is, originally we could have changed the phase of our condensate, of our vacuum expectation value, without changing the total energy. If we do that uniformly over space, we get a whole bunch of degenerate states. If we do it slowly over space and time, we get states that are nearly degenerate and represent low energy excitations. In the context of relativistic quantum field theory, these soft modes represent massless quantum, so-called Nambu-Goldstone bosons. In helium-4, they represent something else. First of all, let me say that conservation of helium atoms is not really violated. This is not a proton decay or an atom decay experiment. If we have a finite sample, the condensate is established, atoms can go in and out of the condensate freely, but if they go in at one place, they go out somewhere else. If we draw a Gaussian surface to count charge around our whole sample, no atoms will go in. We'll still have a conservation law, because there's no condensate outside the material. Nevertheless, there's an observable consequence of this mathematical violation of the symmetry, in that transport of the violated quantum number is easy and enhanced. It's easy to move the violated quantum number. If all space were condensed, it really would be violated. What happens instead is that there's rapid transport of the disturbances in helium atom number, and that's what we call superfluidity. Superfluidity is the flow mediated by the soft modes, or Nebuchadnezzar bosons. And the effective theory of superfluidity can be built around that idea. So in particle physics, we have massless quanta. In fluid mechanics, we have superfluidity. They're really the same thing. The classic superconductors are described by a gauged version of this model. Instead of just partial derivative of phi squared, we now have a covariant derivative for a charged field. And we also have the Maxwell term for our gauge field. And now, when we expand the covariant derivative, as we expanded the ordinary derivatives before, we find something rather different. The d mu rho squared terms are still the same, so that massive field is not affected. But when we take the square of the covariant derivative terms and take this, that's real part squared plus imaginary part squared. The real part doesn't change, but the imaginary part squared does change. And what previously didn't have these GV A mu terms now picks up GV A mu terms. That's the only difference. So that's the only difference in the whole thing, is that we add the Maxwell kinetic energy and the kinetic energy of the sigma field, the field which previously made massless particles, which didn't participate in the potential, now gets vector potential pieces like that because of the covariant derivatives. Well, if we define an A tilde field, which is basically what appears here with a different normalization, then this new term appears to be exactly a mass term for the A tildes. And furthermore, the Maxwell term, since it's got these derivatives of the A's, when the derivatives act here in an anti-symmetric combination, it just cancels out. So the kinetic Maxwell terms don't change. We still have a vector field. However, the vector field has acquired mass. And this is the essence of the Brout, Englert, Higgs paper. And you can do it in a couple of lines. And that very deservedly won them the Nobel Prize. So we have a mass term there, plus some extra nonlinear interactions. And as I said, there's no change in the kinetic energy pieces. So it really is just adding a mass. These equations can be used to describe superconductors. In fact, they were used to describe superconductors in the 1940s already by Landau and Ginzburg. So the mechanism was already in place with all the equations for many decades, but unappreciated because no one asked themselves what it would be like to live inside the superconductor. People usually did experiments outside superconductors, and we're interested in how they respond. But if you put yourself inside the superconductor and ask what you're seeing, you see the equations for a massive photon, and the Higgs mechanism, Brout and Englert Higgs mechanism, is right there. So, particle physicists were looking for massive vector mesons and a way to generate non-trivial fermion masses for chiral fermions in weak interactions. It was there all along inside superconductors. As we'll see as this lecture goes on, this is not the last time that things that particle physicists have been looking for are lurking unsuspected or unappreciated inside superconductors. Now, a very interesting philosophical or methodological point is that the major bulk features of superconductors, the fact that there's an energy gap for fermions, that the photon has become massive, all involve removing low energy degrees of freedom. The thing that made the Lambda-Goldstone boson so interesting and supported superfluidity is the existence of massless particles. Now we've gotten rid of the massless particles, leaving no low energy dynamics at all, strictly speaking. So if we didn't have independent access to the electromagnetic field and weak links and surfaces, the superconductor would be featureless. It would be a hard time if you lived. It would be difficult living inside the superconductor to know that you were living inside a superconductor. Fortunately, we do live on the outside, and we can look at the various effects that are quite spectacular, such as levitating a superconductor, but you have to be outside to levitate it. You can make persistent currents and magnets that affect the outside world. You can even make very sensitive detectors of magnetic fields that can follow thought processes as people think. Electrical currents flow and there are magnetic fields, and they can be sensed with these Josephson helmets. But nevertheless, in simple superconductors, there is no bulk order parameter. And one should speak not of gauge symmetry breaking, because if you're inside the superconductor, you didn't know there was a gauge symmetry to begin with. All you see is a massive spectrum. And also mathematically, it's a fact that gauge symmetry is never broken. It's really a theory it's really a statement about Hilbert space being only gauge invariant states, technically, and that cannot be changed. It's a mathematical identity. But we only have to change one letter to make it correct. We don't have gauge symmetry breaking. What we have, as we've seen, is gauged symmetry breaking. And at weak coupling, if the coupling of the gauge field is weak, we can read off characteristic phenomena that arise when we gauge with a small coupling constant a broken symmetry. Let me come back to the point I skipped over, the fermion part. Within the standard model, the fermion part is you start with Yukawa interactions. We expand around our stable but unsymmetric vacuum with a non-zero vacuum expectation value for the scalar field. And then up to these small fluctuations, we get a mass term for the fermion. This additional term is what happens when we have small fluctuations in the magnitude of the condensate. The magnitude in particle physics represents the Higgs field, and this is the coupling of the Higgs field to fermions with a universal value proportional, or universal coefficient, and then a proportionality to the mass. In superconductors, the dynamics is broadly similar, but the details matter here, as you'll see, and lead to some fascinating additional features. In superconductors, we start with an electron-electron interaction and condense Cooper pairs. So what happens when we condense Cooper pairs in a vacuum expectation value here is we have the so-called gap parameter, kappa times the condensate. And that looks sort of like an electron mass. In the context of superconductivity theory, it's precisely the energy gap. It's quadratic in the electron field, so it looks like a mass term, but it's a very unusual mass term because it violates electron number. In fact, it has the same structure as the so-called Majorana mass term, which is postulated to give neutrinos mass. We know that neutrinos now, through oscillation experiments, we know that they have very small non-zero masses. The leading theory of those masses is that it involves violations of lepton number, and that the neutrino mass term is of this Majorana type. So particle physicists are desperately asking the question, are neutrinos Majorana particles? Do Majorana particles exist in the world? And as in the case of massive vector mesons, they are in the world. In fact, they've been lurking inside superconductors all along. Electrons are Majorana fermions inside superconductors. That's the interpretation of the previous equation. The physical signature of this is that, roughly speaking, Majorana fermions, as opposed to ordinary neutral fermions, can annihilate in pairs. So neutrons are not Majorana fermions, because if you take two neutrons and put them together, you get a very different result than if you put neutron and anti-neutron together. But in a superconductor, the electron's charge is shielded and screened by the supercurrents. It's effectively neutral, and not only that, you have a condensate of Cooper pairs floating throughout the material. So having two electrons really is equivalent to having none at all. They can just be an unnoticeable addition to the condensate. And in that sense, the electrons, well, in every sense, the electrons are Majorana particles inside a superconductor. What used to be called the Higgs particle, but that Higgs himself now calls the BEH particle, and I guess it's now official, is a lucky byproduct of the mass generating mechanism. I told you before, I emphasized that in the gauged version of symmetry breaking, there's really no strict signature. There's no massless particles. There's no order parameter in the technical language. However, if the coupling is weak, we can reconstruct what happened based on perturbing around the broken symmetry phenomenology. And it happens that the magnitude of the condensate, our rho field, what we called rho in the previous equations, the one that had the universal, that represented fluctuations in the magnitude of the condensate, and that had these kinds of universal proportional to mass couplings of the two fermions, happens to be something that you can identify. You know exactly what its properties are, because it's all a weak coupling theory. And unfortunately, the projectiles we have available to us, protons, are made out of up quarks, down quarks, and gluons to a very good approximation that have zero mass. And so the Higgs particle, this rho field, doesn't really want to couple to protons at all. Fortunately, some unsung hero realized that gluons indirectly can allow us to communicate with the Higgs particle because gluons very happily couple to top quarks, and then the top quarks are very heavy, so the universal coupling of the Higgs particle to the top quarks is quite substantial. And then the Higgs particle can decay in a way that's very difficult to mimic with backgrounds by a similar mechanism, now into photons. And this is, in fact, how the discovery was made. I'll show you that in a moment. Let me also emphasize that if there are additional heavy particles that so far we haven't had the wherewithal to produce, this might be a way eventually in precision measurements when you compare observed versus calculated production and branching ratios to detect the effects of those particles as virtual particles. If we hadn't discovered the top quark in advance, we could have indirectly gotten evidence for it from the existence of the Higgs particle, for example. So those experiments are not easy, but they can be done. And here is the original discovery plot. You can see that we need tremendous control of the standard model in order to see this little bump, which is the Higgs particle signal, Higgs going into 2 gamma, above the standard model background. But the standard model is great, theory really works, and this discrepancy can be reliably calculated and reliably measured. By now the data is better and the bump has gone up a bit. This is when it was already becoming clear for the first time. Okay, so that's a quick review of the classic theory and also the newly classic application to the standard model. It's been around for a long time, but now experimentally established. The ideas that arose in coming to terms with the classic superfluids, ideas about symmetry breaking and how to deal with dynamics around these new solutions that break the symmetries, are ripe for generalization, and it proved extremely fertile. We learned the lesson that by focusing on symmetry and its breaking, we can generate questions and answers in seemingly far-removed fields, as we've already exemplified, and suggest some of the new phenomena that would occur. We can anticipate some of the things that might occur. Moreover, I've been discussing kind of semi-macroscopic effective theories, simple theories, with brief excursion into actual electron interactions. But Bardeen, Cooper, and Schrieffer gave us a simple, powerful, microscopic understanding of superconductivity that's also easy to generalize and use, and therefore gives us a powerful lever into new physics, as I'll exemplify later in this talk. So, a very interesting and instructive example of this kind of interplay is to analyze the high-density, low-temperature limit of QCD. This means large chemical potential and low temperature. We will see, in the matter of a few slides, that the central hard problems of confinement and chiral symmetry breaking, which are the classic tough nuts that are hard to understand in QCD, but that are non-perturbative, become straightforward in that limit using the superfluidity concepts. So we can actually prove those things, and in fact prove them quite simply. So QCD meets BCS. These considerations, I think, shed considerable light on the issues of what is confinement, as well as a different perspective on what is superconductivity. Because we'll see that confinement and superconductivity are really the same thing. So, stepping back a moment, suppose we were confronted with this question. We're interested in what might happen when we compress hadronic matter to extreme densities. We might be interested in that just as an intellectual problem. We could also be interested in that, of course, because that actually happens inside neutron stars. It's I found it an extremely useful principle in theoretical physics to adopt the Jesuit credo, which is that it is more blessed to ask forgiveness than permission. So in the context, well, that's useful in many different areas of life, but in the context of physics, what it means, I think, as certainly one of its meanings, is that you should ask how things might be as simple as possible, and try that, and see if it goes wrong, or see if you can succeed that way. And then, if it doesn't work, well, you ask forgiveness. So, from the point of view of QCD, of course, the simplest hope is that hadronic matter, which at low densities is very, very complicated, has things not organized into quarks and gluons, but into protons and neutrons, which have very tricky interactions and are complex composite objects, to hope that somehow at high density we can start all over again, as we do at ultra high energies, and work with the quarks and gluons. And when you think about this a little bit, it seems very promising. If we go to very high density and low temperature, the quarks, being fermions, will form big Fermi surfaces, big Fermi balls, occupied states. The low energy excitations will involve small changes in the occupancy near the surface there, but the states involved will have very large energy and momentum. So that's the regime where the effective coupling gets small, according to asymptotic freedom. So it seems that the strategy of starting with quarks and gluons actually is self-consistent. That if you start with that, you learn that the effective coupling is small. So you can start, that's a valid starting point. You can start to do perturbation theory, building on that, figure out what's going on systematically. However, when you actually calculate, you find that there are problems. The coupling is weak, but the diagrams are divergent. They have infrared divergence. So a small number times infinity is still infinity. And unfortunately, so this approach seems to have problems. The gapless, the infrared divergences arise when you're integrating very low momentum modes. And so have small energy denominators. And they arise because there's no energy gap for excitations of the quarks around the Fermi surface, and also because you still have massless gluons in the theory. Fortunately, we have the accumulated experience of mankind in understanding superconductors to build on. The problems I told you about, of having small massless particles around the Fermi surface, massless excitations, and massless gluons, are exactly the same problems as we meet in superconductivity, though we had a massless photon and massless or gapless electrons. And we met the same kind of infrared divergences there, and Bardeen and Cooper and Schrieffer taught us how to deal with those. So we should now look for a generalization of that wisdom to encompass the color degrees of freedom instead of electric charge. So for superconductivity to occur at weak coupling, the necessary and sufficient condition is that there's an attractive force. In the theory of solids, that's very difficult to arrange because electrons really do want to repel each other. So there's a very tricky theory that can give you an effective attraction due to retardation. I won't go into that. The point is that in QCD, it's much, much simpler. Even the most basic analogs of electric forces can be attractive. The reason that electric forces between electrons are repulsive is that if you take two electrons and put them close together, the fields get bigger, and so the energy in the fields, being the square, gets bigger. And that means it costs energy to bring the electrons together. If you bring them together, you get 4 times the field as the fields you might have if they were apart. I'm sorry, instead of having 1 unit of electric field, another unit of electric field, and adding to 2, when you have 2 and square, it's 4. So that's 4 is more than 2. So the energy, field energy is bigger. It's a repulsive force. With quarks, you can add a triplet and a triplet in color, anti-symmetrically, and then it's an anti-triplet which generates fields of the same strength. So now, if you bring 2 quarks together and in a color anti-symmetric configuration, this force is actually attractive. So we can get attractive forces right from the beginning without any tricky lattice effects or retardation or phonons or anything of the sort. Superconductivity is a much surer consequence in this regime. And so we can take the accumulated wisdom and construct a dictionary. What are the consequences of this cross-fertilization? We understand that the infrared divergences that we meet in QCD are the same as the kind of infrared divergences that people met in superconductivity theory, where they're called the Cooper instability. The effect that photons become massive, as I discussed, in superconductivity, and charge gets screened or washed out, is exactly the effect that we no longer have long-range color forces, and the color charges of the quarks get washed out. The effect that a gap opens up in the fermion spectrum, which is in QCD, reflects the breaking of chiral symmetry, characteristic of massless particles. The use of a weak coupling but non-perturbative model in superconductivity becomes the use of a non-perturbative but weak coupling model in QCD. In other words, pretty much the same thing, but it's very valuable to have models where a very small coupling that you can controls and such that you can do controlled approximations, can give you truly non-perturbative phenomena that are calculable. Okay, some technicalities here. Let me focus on the beautiful case where we have 3 massless flavors. That turns out to give an interesting, easily interpreted result. And it's not a bad approximation if we go to very high density and we can neglect the up, down, strange quark masses. So all the consequences of chiral symmetry breaking, changes in quantum numbers, constants, and especially confinement that I'll talk about are consequences of the following simple idea. That if we have pairing of quarks, as we have pairing of electrons in a superconductor, and this is a calculable consequence of what happens at high density with the effective decoupling, then what will happen is we want approximate anti-symmetry in the color indices, as I discussed, but let's allow them to float a little bit. And then we have the flavor indices. We need them in order that this whole thing can be symmetric in interchange, because that turns out to be, when you include spin, what's required for Fermi statistics. And to make it work, then, in the most symmetric possible way, which turns out to be the way that's most energetically favorable, one has a condensate of this form where color indices get put equal in these delta functions to flavor indices. That means that if you just rotate the color indices, the solution is not invariant. These things
condensate will change. If you just change flavor indices, also the condensate will change. So both color and your original flavor symmetries are lost. But what happens is you get a new kind of flavor symmetry where you do simultaneous color and flavor rotations, and that will leave these Kronecker delta functions invariant, as unitary transformations do leave Kronecker delta deltas invariant. The point is, however, that you have to do the color and flavor both at the same time, and for both left and right-handed. So the new symmetry is not the same as any of the old symmetries, but it's a certain cunning combination of them that survives. Here it is with its full glory of indices, and now you've seen it, and now you don't. The essential thing is just that color and flavor get linked and locked, and the symmetries get locked together. This has dramatic consequences. First of all, for the spectrum of the theory. Normally in QCD, it's very difficult to calculate the spectrum, what the low energy excitations look like. In this domain, it's very simple. And absolutely, it's not stunning what comes out. There are basically three kinds of elementary excitations. There are the elementary excitations produced by the quark field, so its quanta. The elementary excitations produced by the gluon field, quanta of the gluon fields. And then the collective modes, like our sigma field before, associated with the fact that we've had some spontaneous symmetry broken. In this case, the flavor chiral symmetry. If you calculate the behavior of these particles under the new flavor symmetry, they're all color singlets. Color is gone. So there's no local symmetry. The gluons are massive. The flavor symmetry is all that remains. If you calculate the quantum numbers of these particles under flavor symmetry, and also their space-time properties, their spin and so forth, you find that the quantum numbers, the characterization, the properties of the quark field quanta match exactly the quantum numbers of the observed octet of baryons. There are 3 flavors and 3 colors, so 9 different quark kinds of excitations you can make. 8 of them match the baryon octet. There's also a singlet, which is heavier. The gluon field quanta used to have only color indices, but no flavor indices, but flavor got locked together with color to make the new flavor. So we have an octet of vector particles under the new flavor. These exactly match the vector meson octet in the observed hadron spectrum. And the collective modes associated with broken chiral symmetry in the usual way are associated with the pseudoscalar mesons. So the spectrum and the symmetry, sorry, I don't know why that faded. The I'll read it. It went by really fast, so I just want to show you that it's there, and then read it. So I can see it, you can't. Since the spectrum and the symmetry of the color flavor lock superconductivity nicely matches the expectations for what we would have in the nuclear physics of this 3-flavor QCD, we're tempted to conjecture that as we increase density in this massless 3-flavor version of QCD, from nuclear density, where we can't calculate, but we have phenomenological expectations based on experimental experience, to ultra-high densities, where we can actually calculate what happens, we find that the calculable things at ultra-high densities match what we expect also to happen at low densities. So we think there's no phase transition at all, that the quark phase is the same as the hadron phase. There's no phase transition necessary. It might seem odd that a quark can have the same properties as a baryon. After all, a baryon is famous for being 3 quarks, and 3 is different from 1. In fact, it's discretely different from 1. So it's hard to see how you get continuously from 1 to 3. But the point is that if space is filled with a condensate of Cooper pairs, which in this case happen to be quark pairs, then pairs come for free, and the difference between 1 and 3 is negotiable. You can smoothly turn from 1 and having a big amplitude to be 1 to having a bigger amplitude to be 3. There's no necessary discontinuity. The other famous feature of confinement that was thought to be very paradoxical in the early days was the fact that quarks have fractional charge. Our theory is built from quarks with fractional electric charge. What happened to those charges in the physical spectrum? Well, the original, here we have a modified U1 because the symmetry of the state with the condensate is not the original color symmetry or the original electromagnetism. The one that survives and gives a massless vector boson is a combination of the two, just as in the standard model, the emergent photon is a combination of what was originally the hypercharged boson and one of the weak isospin bosons. And the original photon was described by this charge matrix. If we consider a gluon, which in color space acts with the same matrix, then acting with these two on a Kronecker delta function, since they're the same, and make a unitary transformation, we'll leave everything invariant. And so the massless vector boson, which we can get by taking a combination of those two, is easily identified as this one. And if we now calculate the charges of things, we take G times what we get from the original photon, and then minus, because the indices go downstairs, the color, the way I've done things, minus E times G times something here. We take the difference between anything here and anything there. We get an integer. Also for electrons, we get just this contribution, but it's already an integer times the new charge, Eg over square root of G squared plus E squared. So, in fact, even though confinement has been implemented by this simple symmetry-breaking superconductivity mechanism, we find that fractional charge is gone. If we measure fractional charge as we should, according to what the photon thinks is the charge, we find that all the particles have integral charge. That's a story that was already appreciated fully by the end of the last century. Now I'd like to discuss, in the few minutes that remain, some new ideas that I think are extremely interesting, that are in their infancy, that are organically related to the themes I've been discussing. So one is superfluids and space-time translation symmetry breaking. In 1964, Larkin, Ovchinnikov, Ferrell, and Fulde, usually in this context lumped together as LOF, proposed the possibility of pairing with electrons that, unlike in conventional superconductors, where you pair electrons with equal and opposite momenta on opposite sides of the Fermi surface, Cooper pairs, you displace the momenta so that K pairs with minus K plus delta, where delta is a fixed parameter. For reasons that I wouldn't be appropriate to go into here, this can be energetically favorable. And in fact, in the 21st century, after the passage of 35 years or more, now there are few probable examples, still not completely uncontroversial, where this may be the case. If you think about what this means, these kinds of states, in these kinds of states, the superconducting aspect, the superconducting order parameter, makes a crystal. Or if it's just a fixed momenta, it makes a traveling wave. If you have a couple of them, you can make a standing wave or even a crystal. So these loft states are a new state of matter that are supercrystals. And I got very interested in the question in the last couple of years of whether one could have a similar phenomena, not in space, but in time, where you'd have crystals in time, where the ground state had this kind of periodicity. And borrowing from Anderson and BCS, we can make simple models that seem to show that this is quite possible. So here's the model. It's not as scary as it looks at all. We have two kinds of fermions, B's and A's. They have different energies, epsilon 2 and epsilon 1 for B's and A's. This is a so-called flat band, so I let the energy be independent of K, just for simplicity. And this is like a game of Jeopardy, where we're asking a question. I mean, we have the answer and we want to ask the question. Find the question to which it is the answer. So the answer is a condensate with non-trivial frequency pairing. The question is, what's the Hamiltonian that gives that? Is it something that's conceivably physically interesting, or not so bizarre that it's discouraging? And so this is the Jeopardy response. We have these two kinds of fermions, and we construct a very, very simple sort of kind of what's called a pseudo-spin model in superconductivity that Anderson introduced as a very simple way of thinking about superconductivity, where you construct spin operators out of the B's and A's. If you think about B's and A's as making a two-dimensional space, you can raise and lower things and make two-dimensional spinor representations, if you like, or angular momenta. And these operators, it's easy to show, satisfy the algebra of angular momentum. So it's very easy to anticipate what Hamiltonians we construct in terms of these operators will have as their ground states. And in particular, if we use this particular Hamiltonian, which has different energies for the B's and the A's. Okay, this counts the total number of particles, B and A. This counts the difference between the B's and the A's, S3. So this gives, the two of them give energies different for B's and A's. And then we construct this interaction just because it's mathematically simple to deal with and not so different from what might have in a realistic model of a material. Then you can see that we can do well in minimizing the energy by letting S plus get a vacuum expectation value, or S minus. Then this will be then whatever that vacuum expectation value is times its complex conjugate. If we have a positive G, that'll be a favorable negative energy. So that's the idea. But then, when we implement that idea, take it one little step further, compute how this S plus evolves in time, we can compute it. Everything is just given in terms of simple spin operators, so there it is. And if S plus is getting a vacuum expectation value, we saturate this equation with the vacuum expectation value, and we find that this phase parameter, which takes us between the different energetically degenerate vacua actually should be changing in time. It's like we have an effective magnetic field acting on the spin, causing it to precess. And there it is. So you can have frequency dependence in a rather straightforward implementation. So if BCS theory is correct, this is a universality class that should be physically realizable. So, in fact, it's more than a universality class. It's a family of universality classes because you can ask about frequency-dependent order parameters across a broad range of possible applications. So, that's that. The other idea I'd like to mention that grows organically out of this kind of thinking about superfluidity and symmetry breaking. I'm very excited. This is a really new idea, just in the last couple of weeks. So caveat emptor, but I'm pretty sure it's right. And in any case, I'm going public with it. If it's not right, please let me know. The axion is a hypothetical particle introduced to explain a striking coincidence in the standard model. The details won't concern us here, but it's the fact that QCD seems to maintain parity and time reversal symmetry very, very accurately in nature, even though we don't have an explanation of why a potential violation that's allowed by general principles in QCD, why it's so small. So there's a fundamental coupling constant whose value is observed to be very, very small. And we don't know why. If we don't have axions, but if we do have axions, then we understand why. This particle is almost a Nambu-Goldstone boson, but its parent symmetry, what's called Peche-Quinn or PQ symmetry, has a small intrinsic breaking through quantum anomalies. And I have to apologize. Obviously, this part of the talk is at a very different level than the previous ones, but so this is addressed to experts. If you're not an expert, relax. It won't take very long. The axion is a BFD. This was a term introduced by our Vice President, Joe Biden. I won't elaborate on what it is, but it means something very important. The axion is something very important, not least because it plausibly supplies the dark matter in the universe. You can ask me about this in the question session if you like. So it's very important to, it's a frontier of research in particle physics and cosmology to see if this particle really exists and is present in the universe as a background supplying the dark matter. Now, if we're interested in probing its possible existence with superconductors, what's crucial is its coupling to electrons. So its coupling to electrons is dictated, as the couplings of Nambu-Goldstone bosons are, by the nature of the symmetry which is broken. So we can imagine that right-handed and left-handed electrons have different Peche-Quinn charges. That's all we have to know. Then we can determine the couplings. So let the couplings be B and C. Let the charges be B and C. And then we can figure out what the symmetry generating current is. It couples to right-handed electron number with some coefficient B, and to a left-handed electron number with some coefficient C. And organizing the terms, we get a vector and an axial vector contribution. The axion, to a very good approximation, couples linearly to the divergence of this current. That's the way Nambu-Goldstone bosons couple to the divergence of their original symmetry current. The vector current is usually ignored and has been ignored in the literature of axions because its divergence normally vanishes. Electron number is normally conserved in empty space. But in a superconductor, the fundamental thing that happens in a superconductor is you have a condensate of electrons And now the vector current is not conserved. So this comes into play, and instead of getting 0, we get, in addition to the usual contribution of axion coupling from the divergence of the axial current, which is this funny coupling involving a gamma 5, which in the non-relativistic limit becomes a spin and momentum dependent teeny-weeny interaction. We get, inside a superconductor, we get this thing. Let me take the divergence. We have pieces that reflect that Majorana mass of the electron that I discussed before inside a superconductor. So, putting it heuristically, the axion couples with a universal strength to mass, not only to ordinary mass, but also to the Majorana mass of electrons inside superconductors. So, knowing the mathematical form of the interactions, we can read off the physical consequences. Let me just put it back up. The axion being a massive field, if it's present cosmologically, will be oscillating in time with a frequency e to the I mt, approximately. So it's a time-dependent field. So we're applying a time-dependent field to the electrons, and that means that we can excite electrons from the ground state over the gap and do something that superconductors don't usually do, spontaneously produce particles. Or to put it in particle physics language, the axion field can be absorbed by an electron in the superconductor, which excites that electron over the gap and produces a very characteristic noise term that we wouldn't normally have at low temperatures. So, I haven't yet explored the numbers carefully and the backgrounds, but this would seem to open up a new detection strategy. In any case, I hope you'll agree that it's a very interesting example of cross-fertilization of ideas. So, let me now conclude. The conclusion is, I think, simple and convincing. The connection between superfluidity and symmetry breaking has had a glorious history, and it's left us a rich legacy of fertile ideas that seems to be far from exhaustion. Thank you.
So, thank you very much for a fascinating lecture. I guess we're running a little bit over time, but let's anyway. If you have a short question or two, please.
Yeah.
Towards the beginning of the talk, you showed a picture of how this Higgs boson can be created and then detected.
Yes.
Basically, the whole analogy was you could have there was an analogy to the superconductor. Is there a similar kind of mechanism you could draw for if you were situated in an actual superconductor, how you could create this kind of gap excitation and how that could decay? Is there some sort of...
The problem in real superconductors is that the kind of excitation that is the Higgs particle in particle physics is a change in the magnitude of the condensate. And you can produce such things, but they produce a very broad resonance that's not very characteristic in a superconductor. So it's difficult. We're not so lucky in being able to get an identifiable phenomenon in that case. There have been some papers in the literature that claim to see a Higgs-like particle-like signature in the superconductor, but it's not the most striking phenomenon by far in superconductivity, and not nearly as striking as it turns out to be in particle physics.
Could you say something more about the detection methods you envisage?
For the superconductor? For the axion?
Yeah.
Oh, well, you take your superconducting material
cool it down extremely, extremely slow, low temperature, so that nothing should happen. And then, according to this, occasionally, for no reason at all, electrons will start to, instead of sitting in the ground state, will start to be excited. And you can draw off noise, you'll have noise currents that are associated with these. If you apply a field, you'll have noise currents associated with these guys. That's a theorist cartoon version of how you might use this detect.
One final question from Maria?
Well, actually, I had a similar question, but I guess since it was asked, then does this new reasoning have any implication on all the current limits on the actual mass, or this would be, you're saying, searching in the window which is left, that this would be a clever way to look for it?
Yeah, this is a new idea. Okay, I may be going way beyond what's actually possible, but what's characteristic here is that the energy that you produce, since the cosmological axion should be moving rather slowly, basically their energy is just the mass energy when they're absorbed. So you'll be able to produce excitations with that energy, not a smaller energy. So you can compare superconductors with different values of the energy gap, or you could dial the energy gap by some appropriate tricks, and you should find that nothing happens. You cross a threshold and suddenly you have a noise current. I'm sorry, I should have said it this way. You have a big gap, you lower it, and when you get to a critical value, suddenly you start to get this noise current.
Okay, one more, and then...
I have a short question. What is the application of this colorless flavor locked phase in reality? And maybe you can tell us what happens inside black hole.
No, black holes don't have any colors. So I'm not optimistic about the application to black holes. But neutron stars, I think, are quite possible. And there's a very large literature on trying to apply this to neutron stars. The crudest thing is that the color flavor locked phase is predicted to be considerably denser than the nuclear phase. So you might have a sudden transition from a less dense phase, still of course very dense by ordinary standards, but less dense, to a much denser phase. Of course, neutron stars are not an easy experimental playground. However, I think there are prospects for big improvements in the future when people start to detect gravity waves. The response of neutron stars to other neutron stars that are spiraling in, or black holes, to those tidal forces depends on the equation of state and their interior structure. And so maybe long after I'm dead, maybe if I'm taking, I exercise and take my vitamins, and if maybe the gravitational wave signals, when properly interpreted and decoded, will be able to tell us what the interior structure of neutron stars is, or give us some information about that, and that would be the kind of application that I could envisage.
Okay, then I suggest we...
Very pleased to hear this very nice expose of old and very new ideas from Professor Wilczek. And we are here in the Oskar Klein auditorium, and I myself am the leader of the Oskar Klein Center for Cosmoparticle Physics. So I think it's quite appropriate for us to hand over a medal that we have. It's the Oskar Klein medal. It's not exactly like the one you got in 2004, it was a Nobel medal.
Well, been there, done
very
that.
nice.
Right.
So, please.
Thank you very much.